Hi, this is Alex's World of Math, and today we're going to go through the binomial theorem. All right, so recall the binomial expansion of this arbitrary term. So you have this general binomial where x plus y is to the raised to the power of n. And notice that this can be expressed as x plus y times x plus y dot 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 times x plus y n times, right? And um, so there's a very cool trick that we can derive the binomial theorem right here. So notice that every single term is going to be a product of one of these individual binomials, right? You have n binomials and um, of x plus y, and then each multiplication, like each term that you'll get, is going to be using one of these terms multiplied by one of each and every other term. For example, remember the FOIL um, the FOIL technique, right? If you had x plus y to the power of 2, you would have this. To obtain one term, you would do x times x, right? And so that's using one term from each of these expressions. And the next term would be x times y, and then you have x times y again, and then you have y squared. And so basically, you had this unique combination occur twice, and each of these occur once. And that's why we have the coefficients 1, 2, and 1. And with the binomial coefficient, you can actually obtain each of these terms. But let's explore how we can derive this using combinatorial argument. So we know that each of these terms are going to be chosen, uh, however many the coefficient uh, is that represents the amount of times that it's going to be chosen. And so say we wanted to sequence, so we know that there's going to be one instance that there's all y's. So let's represent that as y to the power of n, right? You're going to have a y to the power of n because you can do y times y times y. Every single term you multiply with y. So you're choosing y all those terms. So we know that the coefficient is going to be 1 because that's the only instance that it only can happen once, right? You can't choose, like if you chose x for one of those, then you would have n minus 1 y's and 1x. And so how do we derive the coefficient for every single term? Well, let's see. If you wanted to choose, so say you wanted to choose kx's, right? You wanted to choose kx's, so k of these are going to be x, k times. It's going to be chosen k times. This is going to be chosen n minus k times. And so the question is, how do we choose from these n binomials k x's and n minus k y's? Well, remember stars and bars? Remember, if we choose a pile of k, okay, if we have like a pile of n items, and we wanted to choose k of them to be x and n minus k of them to be y, then if we choose k x's and we place that into a new pile, that leaves n minus k y's in the original pile. So if we just choose kx's, then we're done with choosing both of them. Because if we choose kx's, then we know the rest have to be the rest n minus k items have to be chosen as y, right? And so we can use this cool trick to evaluate that for every single term. If you want some kx's, so let's represent this as x power of k, y to the power of n minus k. Um, then the coefficient is going to be just how many times you can choose k items of x, and the rest has to be chosen as the rest n minus k items has to be y. And this is the same thing as choosing n minus k items to be y, and the rest has to be kx's. But for convenience, we can just say this is going to be n choose k. And that's actually just the binomial theorem. You're summing this for every single possible k, starting with k equals to 0 to the power of n. And why does this work when we sum out all the possible k's? Is because remember one of the outliers are having all the k's chosen. I mean all the y's chosen, and the other outlier is having all the x's chosen. And so the k from the x exponent can range from 0, uh, 0 x is chosen, all the way up to all the x is chosen. And so this accounts for all of the possible terms that can be created using this expansion method. And so this is the binomial theorem, and this is called the binomial coefficient. And that's a pretty cool way to prove the binomial theorem.